Well, today our speaker is Andreu, and he will talk to us about joint ergodicity of sequences. So the floor is yours.
Okay, thank you. Okay, so because of Furstenberg's proof of similarities theorem, there's been some interest in understanding when certain averages of functions converge to the product of integrals. That would be the case for that we discussed before for the weakly mixing transformations, right? So, but more generally, what we want to do is, okay, let's just consider something more general than n to n3n, et cetera, and think of expressions such as, I don't know, can you see my mouse, by the way, if I hover around? Yeah, okay. So consider expressions with arbitrary sequences, right? And the problem of joint ergodicity is asking, what conditions can we impose on these sequences A1 through AL such that they converge to the product of integrals? And this convergence should be understood in the L2 norm. So this is exactly figuring out necessary and sufficient conditions is exactly the topic of this talk. And this is a new, very recent result by Francikinakis that I think is very nice and really interesting. And as we will see, the conditions are quite natural, and it's an if and only if, so it's great. Okay, so let's just set down some notation that we'll use throughout the talk. So we want to talk about L2 convergence. So all these functions should be in L2. So since we have a product of functions, the way to make sure of that is for all the functions to be in L infinity. This is going to be always the case. Even sometimes we'll make the reduction that they have norm L infinity norm less or equal to 1. This will be very common. And okay, so the actual definition that we'll use is we say that a family of sequences A1 through AL is jointly ergodic for a particular system, X mu T, if for any F1 FL in L infinity of mu of this system, we have this convergence to the product of integrals. Okay, and we say generally they are jointly ergodic if the collection A1 through AL is jointly ergodic for every ergodic measure preserving system. And here I forgot to mention it, but this system here is assumed to be ergodic. Now, like I said, part of the reason we care about this this problem is because Furstenberg correspondence principle allows us to say that, well, if this statement here too is true, right? If we have this convergence to the product of integrals, then it follows that any set of positive density, positive upper Banach density, contains patterns of the form x plus a1 of n, x plus al of n, just like that. And in fact, we can say more things because the convergence is to what has been called the correct limit, right? So this means that we have large returns even. Okay, some notation we'll use here. You've probably seen it before, but just as a reminder, whenever we write expectation over n, so this bracket n means the numbers from 1 through n, and the expectation here is just 1 over n sum from n equals 1 to n, which is the standard thing for averaging we've used so far. And what I wanted to say is that we use this expectation because it's a little more compact and it just takes less space. And then E of t is just e to the 2 pi I t. This is just very standard notation. Now, so let's start by considering the problem when L is equal to 1. Then we actually have an easy characterization by using the spectral theorem. Namely, we can transform this single operator into average. So we can transform this average of the operator applied to a function to this average of exponential sums, right? So this is e to the 2 pi I, a of n of t. And what we're saying is the sequence a of n is jointly ergodic, or in this case, it's an ergodic sequence, if for every t in 0, 1, excluding 0 and 1, we have this convergence to 0, okay? And this is really, you use the spectral theorem, and if you can show this, you're done, okay? The fact that such sequences exist follows, for example, from work of Bergelson and Young 1, I think. They, for example, showed that certain Hardy field functions are good for equidistribution. I think this is also due to some prior results due to Bosher-Nitzen. And some of the results are also true if you go along primes. Just for the sake of the argument. But now, of course, the real interesting part starts when we have more than one function, right? So L bigger than or equal to 2 is what's missing this criterion. And of course, the reason is that we don't have a spectral theorem for this kind of expression. So what do we know for L bigger than or equal to 2? There are some scattered results, really, mostly having to do with polynomials and having to do with Hardy-Field functions, which are things we kind of know how to deal with because of structure theory that was developed by Host and Kra, right? So the idea is, okay, so the proof usually goes along the lines, we show that if a certain semi-norm is 0, then the averages converge to 0, and then we reduce this, the statement of converging to the product of integrals to an equidistribution result on the null manifold. Okay, that's kind of the strategy that, for example, was used here by Franceschinakis and Kra, where they showed that if we have a totally ergodic system and a family of linearly independent polynomials, we have joint ergodicity, right? But notice that here, it's not something that's for a general ergodic system, we need total ergodicity, okay? Then Franceschinakis proved something that is actually true in general, and it's for Hardy-Field functions. But here, this is not so general. It's for Hardy-Field functions that satisfy some special growth conditions. Okay, but okay, so those are just kind of examples of results that we would like to have in more generality. So what we're going to work towards is having a good criterion that deals with all kinds of sequences at the same time, and it's very abstract. So the first thing to notice is if we start with this expression here and we consider d-dimensional tori, and we want to have joint ergodicity for any ergodic system, then this condition that I have over here pops out very naturally. This limit of the averages for anything in 0, 1 to dl should be 0. Okay, so this just follows if you plug in. So here I have T1 through TL, right? Then all I need to do is have an L-dimensional torus and have a rotation by T1 TL, and then the FIs should just be exponential functions that have to do with the first, the highest coordinate for each of the functions. And then there will be eigenfunctions, so you'll get exactly this, this average over here. So this is definitely a necessary condition that is very natural, but it's not enough, okay? But as it turns out, another very reasonable condition is enough, and that is good enough for DF and OMEGF. And this other necessary condition is something that has to do with semi-norm estimates. So something that I said before, right? Like we can understand things if, provided that some semi-norm is 0, the averages converge to 0, right? So if we have this kind of behavior for the family of sequences A1 through AL, then we sort of have a better understanding of how to deal with them. But as it turns out, this is all we need to know. So having good semi-norm averages, which is, so I will go into detail as to what exactly that means in a moment. And having this equidistribution result, this is all we need for joint ergodicity. And the beauty of it is that this works for any kind of sequence, not something that is easier to understand like polynomials or Hardy-Field functions, right? Those are very concrete, but here we have a very general criterion. So, and also something very nice about the proof is that it does not use structure theory at all. It uses the Host-Kra semi-norms all right, but there's no need to use nil manifolds at all. And instead it uses tools coming from number theory that were developed by Pelouse and Prandeville. So the takeaway is definitely that number theories are our friends, because if we can translate what they do to ergodic theory, we get very nice results. Okay, so the point for, I hope to talk about 2 times, hopefully this will be enough. The goal for me will be to explain how Franceschinakis' result works for a concrete example that he gives. And this example shows how the method works for a particular case. And this particular case is related to the independent polynomials that I talked about before. So the result of Franceschinakis and Kra. And it's this Fürstenberg-Weiss result. This is very concrete. It's just Tnf, Tn squared f converges to the product of integrals if the transformation is totally ergodic. So this is what I want to show to explain how the techniques work and so on. Now, okay, so before I can do that, we need some definitions. So here's and also it's kind of related to the notation I've been using before. So first of all, the spectrum of the transformation T is going to be all the eigenvalues that we can, all the eigenvalues for which there is a function in L2 that's non-trivial, that we have TF equals E of TF. So this E of T, that just means e to the 2 pi I T. And the way we've constructed it, the spectrum here is a subset of 0, 1 because instead of having the spectrum be in S1, we already included with the exponential here. Now, what does it mean to be good for semi-norm estimates, which is what I was discussing before? So here we fix a collection A1, AL, and we say that they are good for semi-norm estimates for a particular system X mu T if there exists some common S such that for any of the F1 FLs in L infinity, if they have 0 semi-norm, 0 est semi-norm, then the averages converge to 0 in L2 mean. Okay, so yeah, sorry. So this is the good for semi-norm estimates for X mu T. In general, we say that it's good for semi-norm estimates without making any reference to X mu T if it holds for any ergodic system. And here there's something I want to mention, that is that seminorms satisfy this property, namely, even if the original measure is not ergodic, the seminorm, the est seminorm of F can be understood as an integral over the seminorms for each mu x in the ergodic decomposition. So that's why it suffices to restrict our attention to ergodic systems, because the property being good for seminorm estimates and the other property, which is being good for equidistribution, do not really depend on ergodicity. So we can make this assumption without loss of generality. And
I have a question.
Yeah.
About that definition for good for seminorm thing. So there exists an S such that if finitely many functions have the S seminorm.
No, just any function, right? So there exists a common S such that if you're any of the F1 through FL and you have 0 seminorm, right? No matter which one you are, F1, F2, whichever one you are.
Oh, I see.
Yeah, if you have 0 seminorm, then the whole thing converges to 0.
Well, Andreu, there is an issue here. Actually, in the ith condition, you just have to go up to the jth term, not all of them. Relation 5 is up to j, not l.
I don't understand. J belongs to this L means J is anything from 1 to L, right?
Yeah. So if you have it for J, you then have the average of the first J terms that it converges to 0. Not all of them.
No, I think it's all of them.
But why would the order matter, Andreas? Because can't you just
No, it matters because it matters. No, it matters because it matters which function has this property, that it has some S seminorm equal to 0. You don't have it for all of them. Maybe we will see in the proof, but this J matters. It doesn't, for example, let's see, this would give you, let me think of an example. Yeah, for example, you are claiming here that it's good for seminorm estimates if one of them, only one of them, has some seminorm equal to 0. This is very weak. You wouldn't get the result. This one wouldn't even give you, I think, the weakly mixing case. Because for the weakly mixing case, you just have to assume that the function of the highest order iterate is the one that has the 0 seminorm. We can continue, but I'm sure about what I'm saying. You don't have that all of them. It's not what I'm saying. It's not exactly that this S step factor that you're gonna get here is the characteristic one. This
right. It doesn't matter that it's characteristic or not. It's just if the function has 0 seminorm, then the averages go to 0. That's all that matters.
Okay, we can discuss this maybe later. But yeah, okay.
Sorry, so
I thought-
while we were talking, I just looked up. So looked up Nikos's paper, and yeah, I think so. Dr. Koutsogiannis. So Nikos has the same notation, but rather than using J, he has used script L and actually has replaced that F by script L. So if we are using J, then yeah, it only goes till FJ, it looks like.
Oh, so you agree with what I'm saying? Okay.
Yeah.
Okay. Actually, that makes me a bit confused, but I think it should be better than this, but okay. All right, and then the equidistribution is as follows. So we say the sequences are good for equidistribution for a system if for any vector in the spectrum that's not zero, we have the averages of the exponential sums converging to zero. So this is the first condition that we were talking about. It's just that we only care about TIs in the spectrum. And good for equidistribution in general is instead of caring about just the spectrum of T, we care about 0, 1 to the L because we don't know what the spectrum could be. So we have to be as general as possible. So just any non-zero vector has to have 0 exponential sums. Okay, so then the theorem that we care about is the equivalence, right? So we have that A1 through AL is jointly ergodic for X mu T if and only if we are good for equidistribution and seminorm estimates, right? And like we talked about before, it's clear that joint ergodicity implies equidistribution. And something that is also true is that we cannot get rid of the seminorm estimates. And this is already clear in the case L is equal to 1, because if we have a weakly mixing but not mixing system, there's a sequence that goes to infinity along which we would only have the result for mixing systems. But if our transformation is weakly mixing but not mixing, then obviously the equidistribution holds because just the spectrum is trivial. There's nothing to check. But we may still have it be the case that the averages do not converge to the integral, right? There can be sequences that are not good for every weakly mixing system, but that are good for mixing systems because they just go to infinity. So we need some other condition, and that's this seminorm estimate. Okay, so.
By the way, because you said that you were confused, what Nikos has is weaker, but what you wrote is it's not that it's wrong, but in some cases it's easier for you to check the other condition, because you can easily show that when you have it up to J, then you have it for all of them. So you can keep this as your definition, but in some cases it helps that you are checking up to the J term, okay? Just to clear the things out. Yeah.
Okay. All right. So, okay. So the example that I wanted to show is the Fierstenberg-Weiss theorem. So here's the precise statement. It says that if we have any system and any pair of L infinity functions, as long as either of them is orthogonal to the rational Kronecker, then the averages converge to 0 in the L2 mu. Here, I didn't write it explicitly, but it means in the L2 of mu. Now, so before I actually go into the details of the proof, I'm just going to talk about what the general strategy overview of the proof is. Okay, so the first thing you can show is that if just go by contradiction, right? If these averages do not converge to 0, then there exists some F2, which we call F2 tilde because it has a special form, with the 3th seminorm being bigger than 0. Okay. I will actually go into a little more detail about this later. And we can assume that the F2 is of this particular form that you see over here. So some averages along a subsequence nk of t minus n squared gk, t minus n squared plus n. So notice that this is F1, and you see the n squared. This is a bit weird, but it's minus n squared because basically we got it from canceling this tn squared here. So that makes sense. And the fact that it's a bar, we'll also understand it later. And this gk here, we can assume that it's some L infinity function. Okay, so this is the first step. And the next step is to use the definition of the seminorms kind of to realize that if you have positive 3 seminorm, or in fact any number of seminorm, then you must have some correlation with an eigenfunction. So more particularly, we have that the limit of the averages of the real parts of these integrals is positive. And here, the delta n1 is defined to be tn1f f tilde, which we'll talk about this more in the future. Sorry, this should not be f tilde. This should be f bar. So this is how the operator is defined in general. So it's tn1f f bar. Okay, this helps with the inductive definition of the seminorms. And the chi-n1 are just some eigenfunctions. I think, yeah, so we're actually going to restrict our attention to the ergodic case. This is just a strategy of the proof, so I'm not going into the precise details. And because we're restricting ourselves to the ergodic case, the eigenfunction can be assumed to take values in the unit circle. Okay, now what I want to do is replace f2 with this limit definition here. This is a weak limit, right? But we can do this because we're already pairing it with the eigenfunction. But then we kind of want to pull out the all of the definition outside. And this is not exactly true because there's this delta n1 operator. But for the sake of the argument, and because this is just kind of the idea of the proof, let's just say that we can actually commute these operators, right? So this whole limit of the expectation and the delta n1. So if we could do that, and we cannot, but let's say it's good enough for what we want to talk about, then everything pops out and we get the real part of what the definition of f2 bar is. So these two functions come into play here. Then the next step that's already kind of written is to cancel the t minus n squared because it affects both these two guys, right? But notice that if we do that, we're adding a tn squared acting on the eigenfunction chi-n1. So it pops out an eigenvalue, this e to the n squared alpha n1. So this alpha n1 is something in the spectrum of t. Okay. Now, we just want to get rid of the eigenfunction. So we use Cauchy-Schwarz to say, well, if this is positive, then it implies by Cauchy-Schwarz that this other limit of averages is positive. And once we have it to this stage, we're almost done because notice that now there's only one operator. There's only one Tn, right? So, and this is just some complex number. So now we can again apply the spectral theorem and Fatou's lemma and some other things to claim that there exists a sequence of positive measures. And we can actually say that all these positive measures have bounded variation, and there's a universal bound that works for all of them. But that's okay, we shouldn't worry about this right now. So basically what happens is that this t to the n becomes e to the n times t, right? And notice that we can combine this with this and we get exactly this exponential sum. So at the end of the day, we just reduce everything to an exponential sum. And now there's something here that's a bit more subtle than it may appear at first sight. I claim that Weyl equidistribution implies that it must be the case that this alpha n1 is in a finite subset of Q. And this is a bit more strict than what we would usually have in Weyl equidistribution, because we know for sure, well, if this is irrational, then it goes to 0, right? So there's nothing to worry about there. But if this is rational a priori, it could be the case that it doesn't go to 0. It just so happens that there's an improvement in Weyl's equidistribution that allows us to say that there's actually a finite subset of Q that we only need to care about. Okay, and I'm actually not going to prove this, but it's part of one of the ingredients that we'll need in the actual proof as well. It's just some number theory result that improves on Weyl's theorem. So okay, so we have this finite subset. We can find a sequence of subsets of 1 through n with upper lower density, so that this equation 8 over here holds, replacing the expectation if we go along lambda n, right? And the advantage of it is that now the chi-n1s only depend on capital N, okay, by combining the previous argument. Then because of that, it follows this. It follows. There's a lot of work here, right? I'm cheating a lot. It's just one can show that you can reduce the step of the semi-norm one more step. So this is basically saying that F2 must have some correlation with the Kronecker, and the F2, the second semi-norm of F2 tilde here can only be positive if we actually have some correlation to the rational Kronecker. And the reason why is because the starting averages are TNF, TN squared F. So if we replace by some F2 by some irrational eigenfunction, then we would still have convergence to zero, kind of by Weil equidistribution, right? So that's what forces the eigenvalues to be rational. And that would be a contradiction, right? Because we're assuming that the averages converge to zero, and that's the end of the proof. So that's just an idea of what we'll do. And okay, actually I'm going a little bit faster than expected, but what I planned for today was just to do the first two steps, the rigorous steps of the proof, right? So now I just gave an overview. Now we're actually going to see how it all works rigorously. So, okay. So we start with the averages for TNF, TN squared F, and we ask what happens if this does not converge to zero, right? We want to, this is kind of what we're working towards. We want to find a special function F tilde that has this form that will be more convenient to us. So how do we do that? But notice that first, I'm not even really involving the semi-norms. So here's the result. Suppose that we have a system and two functions in L infinity such that the averages of interest do not converge to zero. Then we claim that we can assume that the F2 has a special form. Namely, we claim that there exists a sequence going to infinity, a bunch of L infinity functions that have norm less than or equal to 1, such that this weak limit makes the strong limit not go to zero. Okay, and this is exactly the form that we talked about before in the general overview, right? T minus n squared gk, the gk's have norm less than or equal to 1, and then T minus n squared plus n, F1 bar. This should be bar, I think. Okay, so how do we prove this? This is actually just by contradiction. There's nothing too bad going on. So we're going to assume that F1 and F2 have L infinity norm less than or equal to 1. This is without loss of generality, nothing big going on here. And now what we're going to do is we're going to consider the averages that we care about, right? We said that we're going to be able to find an F of this form, right? So what we're going to do is say, okay, so we're going to consider all possible subsequential limits, and here by limits, I mean weak limits of these averages, right? These are the averages of interest. Here, Gn is in L infinity, and Gn has norm less than or equal to 1. And that's kind of what we want to obtain, right? So what we're going to do is say, okay, we fixed the F1, so we're going to consider the span closure of all the weak limits of these sequences, okay? So this is a humongous space. But now we claim that if F2 is orthogonal to this space that's determined by F1, we converge to zero. And this, as it turns out, this is going to be enough for what we want. And indeed, so we just proceed by contradiction. So suppose that these averages do not converge to zero in L2, then we can find some positive number and a subsequence along which we have the averages be bigger than or equal to A. Now, if we let the GKs be just these averages along the NKs, notice that just by definition of the L2 norm, if I square it, then if I call GK this, just putting a bar means that these expectations are bigger than or equal to A squared for any K, right? This is just unwrapping the definition, nothing weird going on. Now, I can assume by passing to a subsequence if necessary that these averages converge. Okay, so I'm canceling the Tn squared here, right? And I get T minus n squared GK, T minus n squared plus n F1, right? And then the F2 is all by itself. It's not being averaged, not being acted by T, nothing. So let's just take a weak limit of these averages. They're bounded by 1, so all of this makes sense. And notice that whatever weak limit we have, it's something that's in C of F1 by construction, right? That's why we define C of F1 that way. But now, because of this inequality 10, it follows that if we just take the limit, then F2 is going to correlate with this F bar. So this integral is not 0. Okay. But now it follows, so this is the end of the proof, right, of this claim. But now, because the claim is true, we're deducing that if we let this represent the orthogonal projection onto this subspace, right, because notice I said span and closure, but this is closure in the L2 sense. So this guy here, you can see it, you can think of it as a projection. So if from F we subtract the projection onto this subspace determined by F1, we converge to 0. And now by the claim here, right? Because if we are orthogonal, then we converge to 0. So we might as well subtract the projection. But now at this point, all we have to do really is we just unwrap that, well, if we don't converge to 0, then it must be this projection that is making us not converge to 0. And if we're not converging to 0, by passing to a subsequence if necessary and doing a bunch of approximations, it must be that something from the core of the way we generated C of F1 is not having us converge to 0. But then notice that we define C of F1 to be closure of linear combinations, right? So what I'm saying with the approximation argument is that we just get rid of these words and we find an F2 of the form that is desired, right? So we have convergence not to 0 for the F2 of this form, okay? So this is just the first step. And notice that I didn't involve seminorms yet. So it's just, if we don't converge to 0, we have a special form for this to happen, okay? And all right, and then just the other thing that I wanted to say, this is something very standard, so I'm not going to really go into details here. It's just if the 3th seminorm of F2 is 0, then we have convergence to 0 for these averages. And the way you prove this is really use van der Korpe trick once, and then by appropriately canceling the Tn squareds, you see that you converge to 0 exactly if one of these averages converges to 0 in L2. But now all of these are linear, and it's an, b, and cn. So it's a known fact that the number of terms tells you exactly the norm of the seminorm, the number of the seminorm, such that if this seminorm is 0, then these averages are 0. But by van der Korpe trick, if these averages are 0, then these averages are 0. Okay. And then, okay, actually, I'm going to stop here because that's all I planned for today. It's kind of the midpoint. What do I wanted to say? Yeah, and then what we're going to do is we're going to combine all of this and start getting into the point where we see that not convergence to 0 means that we are actually correlating with some eigenfunctions. Okay, so I'm going to stop here and let me know if you have any questions.
Can you take it to the where step 1 started? I just wanted to see. No question. I just wanted to see it. Thank you. So step 1 was about if my averages don't go to 0, then F2 must have a specific form.
Yes.
Right?
Yes. Exactly. And then we use this form later on to get the correlation with the eigenfunctions, and then we keep building on that. But yeah, I guess the main takeaways here are, so basically the meat of the argument is going to be to show that if we have positive 3th seminorm, then we can reduce it to the 2nd seminorm, and then we can apply a bunch of Weyl equidistribution results to show that it can only happen if we have non-trivial rational Kronecker projection. Okay. And as for the general result, it kind of works like this as well. So you kind of show that, well, if you have semi-norm control and we're not converging to zero, then it must be that some semi-norm is not zero. Then you reduce it to talking about, you just keep going down. So that's the idea. If the Sth semi-norm is zero, because you have the nice equidistribution result, you can keep going down in semi-norms until you get to the integral, and then it's an easy way to derive the contradiction from there. But actually showing that you can reduce the step of the semi-norm, that's really hard, and that's where the main argument will come in.
Thanks. I'm good with this page now. Thank you.
Okay.
Yeah, very nice. I think in the last argument you're using van der Kolk twice, though, not once, right? Yeah,
Twice.
Square. Yeah. But yeah, I mean, it's just calculations. You are canceling first the TNs and then.
Yeah, first the TNs and then the TN square. Yeah, you're right. You're right.
But Andreu, let's say that you wanted to do it for more terms. Similar, but there it's gonna be harder for you to control the
for the
step.
polynomials, a similar argument can work, but then it's much harder because notice that I said here before that this alpha n1 comes from a finite subset of Q.
Yes.
You need to generalize this, and this is hard. This is hard number theory. However, for the general result that doesn't involve rational Kronecker, right? Because if we have convergence to the product of integrals without any total ergodicity assumptions, we don't really need to be concerned with whether it's a rational Kronecker or not. This whole number theory does not come into play. It's not necessary, actually. So in order to prove this main theorem here that I talked about, you don't really need the Weil equidistributions result at all. These are only necessary if you wanted to do more terms here and more complicated polynomials, then yeah, you need better equidistribution results. But I think that the same method works too.
That's good. Good. Thank you.
And as you will see, so of course I'm not done yet with the proof or anything, but you will see that we're not really talking at any point about Dil manifolds. So that could be another way to prove this result. That's how they do it in the paper with Francikinakis and Kra. But it's not really necessary here at all. So I think that's quite a nice improvement.
And it's amazing about what results Nikos get in this paper.
Yeah. I think so.
Yeah, it's shocking actually. Very nice. So I think that he is obtaining any known class of functions.
Yeah, because
all of them, and also is answering some conjectures from Bergerson, Joel, and Florian. That's crazy. Yeah, he's getting everything.
Yeah, what's amazing from here is that it reduces everything to showing that you have the equidistribution, but the equidistribution was always going to be part of the game, right? Because if you're going to have convergence to zero, then of course you should check it on tori, right? And then that's kind of something that is studied a lot, and you have a lot of results from Buscher-Nitzen and other people that you can use. So that one is fine, but then you're like, okay, but how do you deal with just more complicated systems, right? And as it turns out, it's just, okay, if you can deal with the weakly mixing case, you're done. And I say that because if you can deal with the weakly mixing case, you can usually just reformulate the proof you have to convergence of the product of integrals for the weakly mixing case in terms of seminorms. Namely, if a seminorm is zero, you converge to zero. You can usually reinterpret the theorems for weakly mixing in this case. So basically what he's showing is it's also along the lines of Fierstein, right? If you have it for compact systems and you have it for weakly mixing systems in a way that this makes sense, right? Then you can show it. Yeah. I think it's amazing.
It's really nice that you explain it so nice for people like me. You know, it's like so nice. Thank you.
Should I stop sharing my screen or?
So I guess we can stop also the recording. So
Okay.